The internet moves fast. Billions of packets travel every second. They cross oceans. They pass through routers and firewalls. They move through wireless airwaves and fiber cables. The network is chaotic. Packets get delayed. Packets get dropped. Yet somehow, your messages arrive safely. Behind this miracle is a small and elegant structure. The TCP packet. It is quiet. It is simple, but it is one of the most important engineering designs ever created. In this video, we slow everything down. We freeze a single TCP packet in midair. We rotate it, we open it, and we explore every field inside it. By the end, you will understand why it works, how it maintains reliability, and why the internet depends on it. To understand the TCP packet, we must understand the problem it solves. The internet is built on IP. IP is unreliable by design. It does not guarantee delivery. It does not guarantee order. It does not prevent duplicates. Imagine sending a book through a postal system. Pages arrive out of order. Some pages never arrive. Some pages arrive twice. That is how IP behaves. TCP fixes this. It adds reliability. It adds ordering. It adds flow control. It adds congestion control. It adds connection state. TCP turns an unreliable network into a reliable stream of bytes. And it does this using the fields inside a single TCP segment. A TCP packet has two main parts. The first part is the header. This is the control center. It contains ports, sequence numbers, flags, window sizes, checksums, and more. The second part is the payload. This is the actual data. It could be HTML, JSON, video frames, SSH commands, anything. The header is usually 20 bytes. With options, it can grow to 60 bytes. Every field has a purpose. Every bit contributes to reliability and performance. At the top of the header are two 16-bit fields, the source port and the destination port. Ports identify which applications are communicating. Think of the IP address as a street address. The port is the apartment number. Without ports, your computer would not know where to send incoming data. Your browser, your SSH session, your email client, your game, your background services, all of them depend on ports. Ports allow thousands of connections to exist at the same time. Now we reach the heart of TCP, the sequence number. TCP treats data as a stream of bytes. Every byte has a number. The sequence number tells the receiver where this segment fits in the stream. This is essential. The network does not guarantee order. Packets can arrive early. Packets can arrive late. Packets can get lost. The sequence number allows the receiver to rebuild the stream. It detects missing data. It detects duplicates. It restores order. Even if packets arrive like scattered puzzle pieces, the sequence number puts them back together. If the sequence number is about sending, the acknowledgment number is about receiving. It tells the sender what has been received. It says, "I have everything up to this byte. You can continue." This creates a feedback loop, a steady rhythm, a heartbeat between both sides. The acknowledgment number helps the sender adjust its speed. It helps detect loss. It keeps the connection synchronized. This is the foundation of TCP reliability. The data offset tells the receiver where the header ends and where the payload begins. Because TCP headers can include options, the size is not fixed. This field ensures the receiver always knows where to find the data. A small group of bits is reserved for future use. They are always 0 today, but they allow TCP to evolve without breaking compatibility. Now we reach the most iconic part of the header, the flags. Each flag is 1 bit, on or off, true or false. Together, they control the entire life cycle of a TCP connection. The URG flag marks urgent data, rare today, but historically important. The ACK flag confirms receipt. After the handshake, almost every packet has this flag. The PSH flag asks the receiver to deliver data immediately, useful for interactive sessions. The RST flag resets a connection, used when something unexpected happens. The SYN flag starts a connection. It is part of the three-way handshake. The FIN flag ends a connection. It closes the session gracefully. These 6 bits guide the connection from birth to shutdown. The window size controls flow. It tells the sender how much data the receiver can handle right now. If the receiver is busy, the window shrinks. If it is ready for more, the window grows. This prevents overload. It prevents buffer overflow. It prevents packet loss. With window scaling, TCP can support very large windows. This is essential for high-speed networks. The checksum protects the segment from corruption. It covers the header, the payload, and a pseudo-header with IP information. If a bit flips during transmission, the checksum reveals it. The packet is discarded. TCP resends it. This ensures that corrupted data never reaches the application. The urgent pointer is used only when the URG flag is set. It marks the end of urgent data. It is rarely used today, but it remains for compatibility. TCP options make the protocol flexible. Common options include the MSS option. It tells the other side the largest segment size. The window scaling option. It allows windows larger than 65,000 bytes. The SAC option. Selective acknowledgments. It allows the receiver to acknowledge specific blocks of data. This improves performance when packets are lost. The timestamp option. It helps measure round-trip time. It protects against old duplicate packets. These options are essential for modern performance. Finally, we reach the payload. This is the actual data being transported. It could be part of a web page, a video chunk, a JSON response, a command in an SSH session, a frame in a multiplayer game. Everything rides inside this payload, and everything depends on the header to deliver it safely. The TCP packet is a masterpiece of engineering, a tiny structure that solves huge problems. It brings order to disorder. It brings reliability to chaos. It brings structure to an unpredictable network. Every time you load a web page, every time you send a message, every time you stream a video, millions of these packets work silently in the background. Now you know what is inside each one, and how this small design keeps the internet alive. Thanks for watching, and I'll see you in the next chapter of this digital adventure.